This is a lecture about aqueous solutions, and it focuses on a molecular level view of dissolving an ionic compound in water. And we're going to talk on a molecular level about what happens to intermolecular forces as a solution is made. So just as a quick reminder, a solution is just another name for a homogeneous mixture. Hopefully you remember there are two types of mixtures. There's heterogeneous and homogeneous. Well, the solution is just a homogeneous mixture. Some of the vocabulary that you'll need to be familiar with in this PowerPoint, and hopefully it's a review. A solvent is what a substance is being dissolved into. In this case, it'll be water. If sometimes it's unclear what the solvent is, for example, air is actually a solution of gases. But if I were to ask you what is the solvent in air, you might not know right off the bat. Well, in that case, the solvent is the component that's there in the largest amount. So in the case of air, the solvent is nitrogen gas. Solute is any other component that's in that solution that's present in a lesser amount. Okay, and then salvation. Salvation is what happens on a molecular level when a solution is formed. And salvation is simply the process of solvent molecules, in this case water, surrounding or kind of making like a cage around the solute molecules. And that salvation is a stabilizing force. Salvation must occur in order for a solute to get dissolved. Continuing on our basic review of solutions, solutions can be present in solid, liquid, or gas phase. Most of the time, if you think about salt water and things like that, we're used to talking about solutions in a liquid phase, but they can be in any phase, okay? So as I said before, air is actually a solution of gases. Carbonated beverages are actually carbon dioxide gas dissolved in water-based solutions. Any type of alloy, and that means a solution of metal, is a solid solution. So for example, bronze is made up of zinc and copper. And you can have a liquid solution. Okay, so ethanol is the active ingredient in alcoholic beverages. Ethanol is completely miscible or soluble in water. And so any type of alcoholic beverage is a liquid-liquid solution. All right, so qualitative description of a solution. We're going to talk about qualitative descriptions as far as their concentration, and quantitative. Well, qualitatively, you can tell somebody, I have a concentrated solution of whatever, salt water or whatever, or I have a dilute solution, okay? And sometimes you can tell simply by the shade of the substance if there's a color involved, like if you make Kool-Aid, for example, if the color is really pale, you can say, okay, that Kool-Aid's too dilute. But on a molecular level, what those terms mean, dilute means there are not very many solute molecules. Okay? Not very many solute molecules. There are mostly solvent molecules. And similarly, concentrated means that there are a lot, or there are more solute molecules or particles dissolved. All right, one final vocabulary term, miscible and immiscible. That C is silent when you pronounce that. So miscible and immiscible refer to liquid-liquid solutions. And it simply means that a liquid solute and a liquid solvent are completely soluble in one another. They make a homogeneous mixture. And so, as I said before, water and ethanol are both liquids. And when you mix them together, they are completely miscible. What's an example of something that is immiscible? Well, oil, liquid oil, and water are immiscible. Okay, they are not soluble on each other, and you'll see the separate layers. I lied. That wasn't the end of vocabulary, sorry. Okay, so saturated, unsaturated. Saturated means that you have dissolved as much of the solute as the solvent will hold. It won't hold any more, okay? Unsaturated means you can dissolve more. It means it hasn't reached its saturation point. You can dissolve more of the solute if you want. The solvent can hold more solute. So if I came with 2 containers, let's say beakers, and I told you they were saltwater solutions, and I asked you which one is saturated and which one is not saturated, you wouldn't be able to tell by looking at them unless I'd really gone overboard and had added so much salt that there was a pile that undissolved at the bottom. In that case, you could tell. But if I was really careful and just exactly reached the saturation point, you wouldn't be able to tell the difference by looking. So what could you do to figure out which one was saturated? That's the type, in this clue curriculum, that's the type of question that gets you thinking, and hopefully you can answer that. But if you can't, if your brain's not awake yet or you don't feel like it, I will tell you right now, if somebody asked you to do that and you had access to more sodium chloride solid, you could just sprinkle in more of that into each of the containers, right? And swirl it around. And the container that accepts more of it, that dissolves more of it, was the unsaturated one, right? And if it is a saturated solution, you add more of the solute, it's just going to sink to the bottom. It's not going to dissolve. All right, so we're going to start getting a little bit into the quantitative aspect of making solutions. So here's a kind of a thinking question for you. If I took 5 grams of table salt, sodium chloride, and I dissolved it into 100 grams of water, what would the mass of the resultant solution be? This isn't a trick question. It's a serious question. So pick one that you think would be the case. Well, do you remember the law of conservation of mass? The law of conservation of mass tells us that we can neither create nor destroy mass in a regular process. And therefore, the solution would be exactly 105 grams. Okay, no trick there. The reason I'm introducing this is we're going to talk about volumes of solution versus volume of the individual components later on. And volume is not necessarily conserved. Okay, so here we go. Solution by volume. Let's say that we start with 5 milliliters of ethanol. It is a liquid, okay, on its own. And again, that's the active ingredient in any alcoholic beverage. And we mix that together with 100 milliliters of water. So volume, we call that a volume-volume mixture. What is the resultant volume? Well, from my hint on the last slide, you probably realize that it's not going to be exactly 105. It turns out that volume is not conserved. There's no law of conservation of volume. Sometimes it might be exactly, but in most cases, the volume is going to change, and that is going to be dependent on the intermolecular attractions, intermolecular forces, I'm going to abbreviate that, between the solute and the solvent. You can hopefully envision this. If the intermolecular attractions between, in this case, ethanol and water are very strong, then they're going to want to get really close to each other. And if they pull close to each other, what do you think is going to happen to the volume? The volume is going to shrink because the molecules are getting so close to each other. And so you should be able to predict this by the end of this PowerPoint with some practice, because water is H2O, right? Ethanol also has an OH. So what type of intermolecular forces exist between these two substances? I'm hoping you say hydrogen bonding, which is a really strong attraction between substances. And because that attraction's so strong, if there were no volume shrinkage, that mixture would be 105 milliliters. But because they're so attracted, it's going to be less than 105 milliliters. Okay? Alrighty. All right. So first of all, I noticed that my iPad is not supporting this font or this symbol. So those are supposed to be arrows. There we go. So how are we going to represent when we've made an aqueous solution? Well, the first thing to realize is that AQ, I know most of you will probably say that means aqueous, but what exactly does aqueous mean? Aqueous means dissolved in water, okay? So anytime you see that AQ, I want you to think it's dissolved in water. We're going to shift now to quantitative representations of the concentration of a solute and a solvent. And the units that we're going to focus on for concentration are molarity. So hopefully this is a reminder again. Molarity, the definition is the moles of solute in the liters of the entire solution. Okay, so the most important note to realize at this point is that the denominator of molarity is not liters of solvent. It's liters of the solvent and solute combined. So anytime you see solution, that means solute and solvent combined. All right. Because of that particular definition of molarity, where the denominator is liters of the entire solution, we have to be very particular as chemists in how we make up a certain molarity solution. And this could possibly be a question on a quiz or test, so this is something you need to make sure you understand. First of all, this is a quantitative concentration, and so that means that chemists are very, very careful to be very precise and accurate. And one way to do that is to use a volumetric flask. A volumetric flask looks like this if you're not familiar with it. They are hand blown and they have a precision typically of 1/100th of a milliliter. Okay, so if you use these in the lab, be really careful. They're expensive. There's usually a little etched line at the top of the neck of a volumetric flask that tells you when you have reached the precise exact volume. So anyway, making a certain molarity solution, you want a volumetric flask. The first thing that you want to do is, of course, you calculate the mass of the solute that you need for the certain molarity solution, and you go ahead and add that to the volumetric flask. Now, this may seem silly, but it's important. This little symbol that didn't come through is a little squiggly line meaning about, okay? Fill the flask then roughly half full with the solvent, in this case, water, and swirl the volumetric flask around until all of the solute is dissolved. Why do we do that? Because the solute takes up volume. When it dissolves, it's going to take up volume. And so you want all of it dissolved so that when you precisely add drop by drop solvent at the end, that the solute is all dissolved and that you get exactly this volume of the entire solution. And again, hopefully you know this already, but anytime you're measuring out the volume of water in particular, water makes a meniscus, that curved surface due to intermolecular forces again. But anytime you're dealing with a meniscus and measuring volume, you want to measure at the bottom of the meniscus. Okay, the bottom of the meniscus. Alrighty. So here's a question for you. It starts with some easy calculations for molarity, and then we'll ramp it up a bit. Hopefully this is a review for you. So what I would like you to do is turn off the video and see if you can do this calculation yourself. Of course, you're going to need a periodic table. Anytime you're taking a chemistry class, you should have a periodic table handy, either printed out or a tab open on your computer. So this asks, how many grams of sodium chloride, and I was nice and gave you the molar mass, are required to make 1 liter of an 0.1 molar solution. If you think you can do that, go ahead and try it on your own. Otherwise, I'm going to walk you through now. So what I do for pretty much every calculation I do is I write out the formula I'm going to use first. Okay, so molarity, which is represented by a capital M, equals moles of solute divided by liters of the entire solution. For those of you who may be algebra challenged, here's a little triangle that makes your rearrangement of equations handy. And so if you're going to use this triangle, you're going to have to memorize it. And the only important thing is to remember that moles is on top here. Doesn't matter the order of the molarity in liters on the bottom. But if, in case you don't know how to use this formula, what you do, or this triangle, type of triangle, what you do is whatever you're trying to solve for, you cover up. So if you were trying to solve for moles of solute, you would cover that up, and that would tell you that the moles of solute equals molarity times liters. Okay, right here in the bottom. On the other hand, let's say that the problem asks you to solve for volume, in other words, liters. You would then cover up this section of the triangle, and that would tell you then that liters would be equal to moles divided by molarity, just like you see here, moles divided by molarity. Okay, anyway, so back to the problem we are trying to work on. This problem is asking you for grams. Okay, this formula doesn't have grams, so you have to ask yourself, where can I get grams? Easily. Can I get it from molarity? Can I get it from volume? No, you can easily get grams from moles, right? Okay, so we've got to do that first, or we're solving for moles, basically, because that's going to give us grams. So let's go ahead and plug in what we know. We know that the molarity of the solution is 0.1, and we know that the liters of the solution is 1.0. So from this rearrangement of the equation, we know that the moles of the solute are 0.1 moles. Okay, now from that we can find grams. And this is a very basic, simple molarity calculation. I would actually rank it as a 2 in difficulty on the scale from 1 to 5. So this is something you need to make sure you are really comfortable with before you move on. And again, there are worksheets that are posted in our D2L. So we have 0.1 mole of sodium chloride. If you remember your dimensional analysis and conversions from 1211, I'm just remind you, you always want to match units on the diagonal so that they cancel out, and you want the molar mass on top, 58.4 grams per mole. So this conversion factor is the molar mass for sodium chloride. So when we go ahead and do that calculation, we get that we need 5.84 grams of sodium chloride to make 1 liter of a 0.1 molar solution of sodium chloride in water. So the correct answer, right here, B. Let's try another one. This one tells you the amount of grams you start with, and the total volume of the solution, and the molar mass of the solute. So this one is another very easy one. Go ahead and make yourself write out, show your work. Remember, you're going to be expected to do that in a test. Be careful of units. Make sure you know how to show all your work and circle your final answer. So I would turn off the video because I'm going to start working through it now. I'm going to start, as always, by writing the formula. Molarity equals moles over liter. Then I'm going to plug in what I know. Okay, I don't know moles yet, but I know that I can find moles from grams. So down here, I'm going to put 5 grams of the solute. Doing dimensional analysis, I know I need grams in the denominator so that it cancels out. And I'm trying to get to moles. So whatever you're trying to get to goes in the numerator. And any type of conversion factor that involves moles is typically the number 1 goes in front of mole. And let's see, molar mass of this solute is 110. So this is our conversion factor now. There are 110 grams in 1 mole of this solute. So when you go ahead and do the calculation, you get that there are 0.045 moles of this solute. So now I'm going to go back to the equation and plug in what I've just calculated. 0.045 moles. And let's see, do I know the liters? The problem tells us that we have 100 milliliters, and so this equation, it's important to remember that you have to have your volume in liters, not milliliters. And so we've got to convert that. So again, using our dimensional analysis, there are 1,000 milliliters in 1 liter, okay, which means that 100 milliliters equals 0.1 liters. So I'm going to go ahead and put that information in, and then I'm going to go ahead and do this calculation. And the answer is molarity equals 0.45. Now, you can either use the capital M as your units, or you can write out moles over liter. Either one is perfectly acceptable for units. So A was the correct answer in this problem. And here it is worked out a little bit neater. All right, so we're going to shift to different units, percent by mass. Percent by mass is pretty much what all consumable items that you buy at the store, if you turn to the ingredients label on the back, they're almost all in percent by mass. So it's a handy unit to know how to deal with. The breaking down percent by mass, it is equal to the mass of the solute. Notice the solute always goes on top when you're talking about concentrations. Divided by the mass, again, of the entire solution, okay? Which means that in the denominator, you need the mass of the solute added together to the mass of the solvent. Sometimes you'll need density of the solution. Density can be used as a conversion factor to switch back and forth between the units of grams to the units of milliliters, depending on what you need for an equation. So if you want to be brave and try this one, we're now at a difficulty level of 3.5. Go ahead and turn off the video and try it, and otherwise I'll be working it out for you. Let's go back and read the question and see what we know that we can put into this formula. Let's see, do we know mass of solute? Yes, we do, yay. So we have 5 grams of the solute, so we've got the numerator. So now on the bottom, we need mass of the entire solution. So sometimes you're going to have to literally find the mass of the solute and the solvent separately and then add them together. In this case, since they gave us the total volume of the solution and we have the density of the solution, we can convert from the milliliters that we have now volume to grams by using density. So let me show you how to do that. If we have 100 milliliters of the entire solution, and we know that the density of the solution is 1 gram per 1 milliliter, okay? So milliliters has to go in the denominator so that it cancels. And this density value tells it's 1 to 1. So we have exactly 1 milliliter for every 1 gram. Okay, so basically anytime the density is exactly equal to 1, you can simply change the units to milliliters to grams without changing the quantity. So that tells us, and pure water, by the way, has a density of 1. So any kind of dilute solution that's made from water will have a density really close to 1. Most of the time you can actually assume that the density is exactly 1. So now we know that the mass of the entire solution is 100 grams, okay? And one of the things I forgot to put over here in the formula is anytime you have a percent, you need to multiply by 100. So here's the calculation worked out a little bit more neatly. And the answer is, after you multiply by 100, 5%. One more formula that we're going to learn here is formula for dilution, which you may already be familiar with. Just in case it rings a bell, this is probably the most common form of it. M1V1 equals M2V2, and capital M being the molarity, moles per liter of a solution. Volume we'll think of as liters. And what this is telling you, if you look at it this way, liters. What this is telling you, what do you get when you multiply molarity times volume? Okay, you get moles. So what this is telling you is when you dilute a solution, the moles that you have doesn't change. So if I have a very concentrated solution and I simply add more water to it to dilute it, okay, my volume changes and the concentration, the molarity change, but the number of moles that I had stays the same. And that's really where this formula comes from. This slide is just emphasizing what I already said about dilution, that if all you're doing is adding more of the solvent, you have the same number of particles, therefore the same number of moles of the solute. But again, your volume has changed and the concentration has changed. So here is the dilution formula, M1V1 equals M2V2. So you literally, when you have a problem that gives you either two different concentrations or two different volumes, that is likely a dilution problem, even if it doesn't mention dilution. And anytime that happens, you can use this dilution formula. The main trick or thing you have to watch out for is that you keep the correct molarity that goes with a particular volume, that you keep these paired correctly. Here's a quick conceptual problem. I had mentioned earlier in this semester that we do a lot of molecular level interpretations of things going on, and this is a good representation for a solution. So the top image represents a bunch of ethanol molecules. You don't need to remember that name in the formula, but just to let you know, C2H5OH is the chemical formula for ethanol, and it's the ingredient, again, in alcoholic beverages that we drink. So here's ethanol molecules. The H2O molecules are left out just for simplicity. And so if that was the representation for a certain concentration of solution, and then you dumped in more water, which one of these three images on the bottom would best represent the diluted solution after you've added the water? So you're going to have a more dilute solution, which means you're going to have less solute per unit area than you did with the more concentrated. So hopefully this was quite easy for you and you selected C. It just has fewer ethanol molecules in the same volume. All right, so here's your sample problem, which, as always, I want you to try to work out on your own. Turn off the video, because I'm going to work through it right now. All right, so I realized by reading this that it's a dilution problem, and so I'm going to write down the formula that I'm going to use, and then, as always, I'm going to try to plug in what I know. It doesn't matter which solution, the dilute or the concentrated, that you call M1 and V1, as long as you keep the correct molarity with the correct volume. So I'm going to use the original concentrated solution. I'm going to call it M1V1. And so M1 is 0.5 5 molar. And the volume that I have of M1 is 100 milliliters. Now, what's really nice about the dilution formula is because volume shows up on both sides, it doesn't matter what units you use for volume as long as you use the same units on both sides of the equation, because those units are going to cancel out. So I'm going to keep it in milliliters because it's a lot easier. If you convert it to liters, you'll still get the right answer. All right, so this is M1V1. What am I trying to solve for? I'm trying to solve for the molarity of the diluted solution. So I'm trying to solve for M2. What is V2? I'm going to pause for a minute because this is slightly tricky. So read over the question again carefully and ask yourself, what is the volume? This is the total volume of the diluted solution. Be careful because that's what V2 represents, is total volume of the diluted solution. And I'm hoping now with that hint especially that you realize the total volume of V2 is 100 plus 50. In other words, 150 milliliters. Be real careful. That shows up frequently in dilution problems. And so now, if I want to simplify, I'm going to, let's see, I have 50 on the left side equals M2 times 150. And so dividing both sides by 150, right? I get the M2, the molarity of the diluted solution, is equal to 50 divided by 150, which is 0.33 molar. So since it's a diluted solution, you certainly expect the concentration to be less than the original one, and it is. So you can kind of check your work. And that's it for this introductory PowerPoint on solutions.